So hi everyone, welcome to my YouTube channel. Myself Sanjeev Reddy. I am from Sri Venkateswara College of Engineering, and today my topic is exploring the Klein 4 group definitions and examples. Exploring the Klein 4 group definitions and examples. Welcome to this presentation on the Klein 4 group, often denoted as V4. We will delve into its fundamental structures and explore its significance within the realm of abstract algebra. This versatile group provides a stepping stone for understanding more complex algebraic concepts. Definitions of the Klein 4 group. The Klein 4 group or V4 is a group with exactly 4 elements, typically represented as E, A, B, C. Here E serves as the identity element, meaning that when combined with any other element, it leaves that element unchanged. A defining characteristic of V4 is that every non-identity element is its own inverse. A square is equal to E, B square is equal to E, C square is equal to E. Furthermore, all elements within V4 commute, meaning the order of operation does not affect the result. AB is equal to BA, AC is equal to CA, BC is equal to CB. Four elements composed of four distinct elements, set of E, A, B, C. Self-inverse. Each non-identity is its own inverse. Commutative. All elements continue with each other. Group operation table. The structure of the Klein 4 group is best understood through its group operation table, also known as a cycle table. This table visually represents the outcome of combining any two elements within the group, demonstrating key properties such as closure, associative, the existence of an identity element, the presence of inverse for every element. Observe how each non-identity element combined with itself feeds the identity. The symmetry of a rectangle. A classic and intuitive example of a Klein-4 group in action is found in the symmetries of a rectangle that is not a square. Imagine a rectangle in a fixed position. The identity transformation E leaves the rectangle unchanged. A represents a 180-degree rotation around its center. B is a reflection across the horizontal axis, and C is a reflection across the vertical axis. Performing any two of these non-identity operation in succession yields the third non-identity operation or the identity, perfectly modeling the V4 group structure. Identity E, no changing to the rectangle. Rotation A, 180-degree rotation. Horizontal reflection, reflection about the horizontal axis. Vertical reflection, reflection about the vertical axis. Example 2. Bitwise XOR on set of 00, 01, 10, 11. Another compiling example of the Klein 4 group is found in the set of 2-bit binary strings. Under the operation of bitwise XOR, in this context, 00 acts as the identity element. If we assign A is equal to 01, B is equal to 10, and C is equal to 11, we observe that XOR ring and non-identity element with itself results in 00, just like the self-inverse property of V4. For instance, 01 XOR 01 is equal to 00, 10 XOR 10 is equal to 00, and 11 XOR 11 is equal to 00. The example highlights the good presence in computer science and digital logic. Elements 00 identity, 01 element A, 10 element B, 11 element C. Operation bitwise XOR. Example 3. Under component-wise multiplication, consider the set of ordered pairs which yields 4 elements. When these pairs are combined using component-wise multiplication, the resulting structure forms a Klein 4 group. For instance, multiplied by results in which is the identity element in this group. This example showcases how V4 arises in mathematical constructs involving Cartesian products and specific algebraic operations. Properties of the Klein 4 group. The Klein 4 group possesses several distinct properties that set it apart in the group theory. It is an abelian group, meaning its operation is commutative. V4 is also isochromic to Z2 and XZ, the direct product of two cyclic groups of order 2 highlighting its fundamental structure. Crucially, every non-identity element in V4 has an order of 2, reinforcing its self nature. Unlike Z4, the cyclic group of order 4, V4 is not cyclic as no single element can generate the entire group. Abelian commutative operation. Subgroups of V4. Within the Klein 4 group, we can identify several subgroups, which are subsets that also form a group under the same operation. As with any group, V4 has two trivial subgroups, the set containing only the identity element and the group V4 itself. Beyond this, V4 has three distinct non-trivial subgroups, EA, EB, and EC. Each of these non-trivial subgroups is isochromic to Z2, the cyclic group of order 2, demonstrating how simpler group structures can be embedded within V4. Conclusion. The Klein 4 group stands as a fundamental and highly illustrative structure in abstract algebra. It simply eight powerful properties, being abelian, having all non-identity elements of order 2, and being non-cyclic, make it an ideal vehicle for understanding core group theory concepts from the symmetries of everyday objects to complex mathematical aids. Thank you.